So, couple of announcements before we start. First thing is I've created a Google Space, I think, for the so the class timings are every alternate day, 10 to 12. So it's not every day. I saw quite a few of you waiting here yesterday. So and for the ones who are already in the G Space, I have created a meeting that sort of recurs every other day. So keep track of that. And the ones who are not in any G Space or anything, please visit the course website for the exact days on which the lecture is. Okay. Uh, Other than that, for today's lecture, so this would be the reference and the reading material. So this is a game theory and mechanism design book by Narhari. Narhari is a professor at IISc. He's the one, he's sort of a very big name in game theory in India, and he has got a lot of seminal contribution. And one of his student. So here, so I have referred to chapter 1, 2, and 3 of this book. Other than that, there is algorithmic game theory book by the gods of game theory. Noun Nissan, Tim of Garden, Eva Tardos, and Vijay Vajrani. So there's a non-printable version available online. So that chapter one, so it covers a lot of things. A lot of authors have sort of contributed to this book. So I've covered chapter one partially for this particular course, and then there are these very nice videos. I probably started with these videos when I was getting into game theory. So you could refer to the week one of these video lecture series as a reference or additional material and additional examples uh, on top of what I'll be covering today. Okay. And the other thing that I wanted to mention is that in the course website and also in the Google Space, I'll upload problem sets after the class today. It's not something that you are supposed to submit or anything, but the idea is that the assignment questions will be from these problem sets. So if you keep solving these problem sets after every lecture, for you, solving the assignment will be very easy. It will be just a couple of questions from all these problem sets, slightly modified, right? And since game theory has a lot of notations involved, I suggest that you do attempt the problem sets and any questions or any doubts, feel free to ping regarding clarification of notations or other things. So yeah, so that's all with the announcements. If anybody of you has any questions or doubts, anybody online as well. Yes, go ahead.
Ma'am, just an operational thing. Since you're pausing, I might as well ask it. Could you turn on noise cancellation in the Google Meet settings? There's a bit of wind noise that's coming in while you're speaking. I think that noise cancellation might help. Yeah, in Google Meet audio settings, there's an option. Not here, ma'am. Three buttons beside the red, the three buttons on the to the left of that. Yeah, under there, if you go to settings, under mic, there's an option for noise cancellation. Could you turn that on?
Okay,
Yeah,
is it
thanks.
better now?
It's much better. Thank you.
Okay. Okay. So, in the last lecture, a bit of a recap. I don't know how many of you remember, but we saw what multi-agent systems was, and the most important aspect about multi-agent system is agent interaction. And what helps us model agent interaction? It's game theory, which is why so we need game theory. And we also saw how game theory, what is the role of computer science and AI in game theory, and the other way around. There is some aspects of game theory that could help model things in computer science and AI. So that's what we saw in the last class. And this class, what we'll see is we'll see some examples of certain games, and how do we model these games? We'll see some simple ways of modeling these games. What really are games, to be honest, that will be clear today. And there are some proper, proper ways or formats in which the games are modeled. One format is the strategic form, or the normal form, or the matrix form. There are so many names to it. And the other is the extensive form. Extensive form is slightly more complex than the strategic form. We'll see how. These are the two kinds of modeling that we will see today. And we'll also see how they are related to each other. And what are the key elements of a game or required to model a game? What are actions? What are strategies? Are actions and strategies the same, or are they different? What's the relation? And what are utilities? So by the end of this lecture, you should definitely get these 5 things in your head. What is a strategic form? What's an extensive form? What are actions, strategy? How are they similar? How are they different? And what are utilities on a very high level? In the next lecture, I'll actually define what utilities. So game theory, like
Good morning, ma'am.
Good morning.
I wanted to ask a couple of things in the previous class. So you explained about that traffic system, which was like became unmanageable.
Right.
So by shutting off one particular road, things became easier. So why that thing happened. Second, connected to this rational behavior of people. So if we talk about rational behavior over a period of time, people would have learned that okay, this could be a shorter route, but it takes a lot of time. So they might as well choose, plan their own path. Took a longer path, which would have taken shorter time. So, and in that sense, the congestion over the shorter route would also have eased. So why this didn't happen if it did not happen?
So the thing is, in the problem sets after today's lecture, I have given 2 problems on Braze's paradox. Once I cover today's lecture and you solve that, you will get concrete numbers as to why that paradox happens. So that I think should be clear as the lecture progresses. And the question regarding rationality, I have not yet defined rationality. The first lecture was more of an overview when I was talking about a lot of things, but I'll concretely define what rationality is, what intelligence behavior is, and how these things actually come into play. So I think you'll have to wait for your answers. Is that fine?
Okay, ma'am. Thank you.
So game theory is a tool to model conflict and cooperation between decision makers, and it provides, we just don't want the agents to interact, we also want to see what is the outcome of such an interaction. So that's the entire goal of this subject. What will happen if we leave people, smart people, to themselves and they interact, what will be the outcome of the system? So that's what we are trying to go at. And now for the first half of the lecture, we'll be covering non-cooperative game theory. And what is non-cooperative game theory? In non-cooperative game theory, the actions are defined for individual players. So every individual player has a set of actions and it is defined only for them, as opposed to a set of actions defined for a group of players. Right? Both of you can form a coalition and take do some action, but that's not what we are talking about here.
So non-cooperation, we can tell that it is totally selfish behavior.
Sure, in some sense, yes. So so they do not coordinate with. Sure. So I'll give you pauses. I'll give some breaks in between my lecture, and that's when you can ask your questions, both for the online as well as offline. So the idea is that in non-cooperative game theory, individual players take actions and they do not coordinate with anyone else. They are making they are solely responsible for themselves. So now let's start with our first game. The first game is the student coordination problem. It's a name that I have given, but generally it's known as it's known by a different term, which we'll be soon see. So there are 2 students, 1 and 2, and they like to do things together. So each of them can decide to do one of the following things. That is, either they could attend the class or they could just chill back and relax in the room. Right? So these are the two actions available to each of these two students. Two actions. Right? And now what I have defined is a matrix wherein I represent. Now it's very important to know how to read this matrix. This is something that we'll be using throughout the course, and we'll be doing numericals and things like that on this. So what I have over here is a row player and a column player. The row player is student 1 and the column player is student 2. The number of rows represent the actions corresponding to the row player, and the number of columns represent the actions corresponding to the column player. Now, in this example, we have two actions corresponding to both of them, so 2 rows and 2 columns. C represents the action attending class, and R is relax in the room, and likewise for the column player. Now, what are these values? So what I'm trying to say, so how do you read these utility values? These are called the utility values or the payoffs that each of these students get. So if both of them chill, both of them go to the attendee class, player 1 gets a utility of 100. Always the first of the tuple is for the row player, the payoff for the row player, and the second is payoff for the column player. That is something we need to know. So if both of them chill, both player 1 and 2 get a payoff of 100. If both of them attend class, and if both of them relax in the room, they get a payoff of 10. Since both of them like to do things together, if one of them is chilling and one of them is doing the class and other is relaxing in the room, none of them get any utility. And likewise for the other. Right? So this is a student coordination problem. It can be represented in the matrix. Row player, the first player, column player, the second player. The number of rows is the action for the row player, and the number of columns is the action for the column players, and these are payoffs. The first payoff, the first in the tuple is always for the row player, and the second is always for the column player. Now, looking at this matrix, what do you think is the best outcome? I mean, what is good for both of them? I don't know if that's true, but if both of them, looking at it, we can easily say that it's good for both of them to attend the class. And what are the worst outcomes?
One of them goes and one of them doesn't.
Yeah. So the worst outcomes are the other. But so if they both of them talk to each other and say, "Chalo, let's go to class," or "Let's stay back in the room," they are somewhat good off. But the idea is here that the students don't communicate. They are very selfish. They are individualistic. They are making their own decisions for themselves. So now, what should they do? What should if I don't know what the other person is doing, what should I do? If I don't know, the second person might go to the class or might stay back. I don't know. Like, I have to make a decision irrespective of that. What should I do? Okay. Why is that?
Yeah, but this payoff matrix is known to them, correct?
The payoff matrix is known to them. It's a complete information set. They know this. Well,
Yeah,
it's
so in
known to
that
both of
case,
them.
in that case, they will both relax most likely because they won't trust the other guy.
They know the payoff is maximum when they go to class. Even if I'm individualistic, the highest payoff I get is when I go to class.
Okay.
Whether the next person is gone or not.
Okay.
So rationally, the other person.
But if the other person doesn't go, then you get a payoff of 0.
But not don't we assume both of them are rational and intelligent?
Both of them are rational
They
and
maximize
intelligent.
their output.
They are trying to maximize their output.
If they're maximizing, then they will go.
Okay. Let's see. So we'll try to. So the idea is to analyze these sort of games. But for today, we'll not see what they will do, but we'll just see how to set these games up and what is the mathematical representation for these games. So these are what are the elements that we need for modeling a game? The elements that we need. Yes, Sanjay. So the set of players N. We need these strategy sets of players, that is S1, S2, S up to Sn. Remember, there are two words that I'm interchanging: strategies and actions. So please keep that in mind. There are payoffs or utilities to each player. And now, how are these utilities defined? So, utilities for every player or for every I is dependent on all the strategies. It's a function of everybody's strategy, what everybody has. That results into one sort of one utility value pool. So that is something that you need to keep in mind. So what is a strategic form or a normal form of a game? It is denoted by this symbol, this weird symbol, the capital gamma. Now that and it has essentially these three elements: the number of players, the strategy sets of each of the players, and the utilities or the payoffs for each of the players. Okay?
Is it a generated set or just a notation?
It's just a notation. It's not a set. So here, what is n here? N is 1 and 2. SI for each of the individual agents are C and R. Utilities are essentially for each of the possible outcomes. The outcome could be that both of them are going to class, or one of them is going to class and the other is not, or both of them are children. So for that, when I say U1 CC, it's always the first of these. Right? For U1, it's the first tuple, first element of the tuple. And for U2, it's the second element of it for each of the possible. So, and the utilities of every player depends on everybody else's strategy. So now this is called the Cartesian product, and S represents the set of strategy profiles. Right? SIs are the S1 is the strategy set of each of the player 1, S2 is of the player 2. But what is a strategy profile is a possible it's an instantiation of strategy for all the players. Right? So you have, this is also called the set of pure strategies or the set of outcomes. Right? It will be clear why it is called pure strategy. That's nothing to do with any purist or anything like that. But so here, for example, in our game, this was the entire strategy profile set that we had, or the different possible outcomes of this particular game. And your utilities are defined over these strategy profiles. Right? For each of these element of the strategy profile, all the agents get derive certain utilities. Okay, now let's begin with the most famous game, which is widely known, the Prisoner's Dilemma. So slightly bringing it to you guys' context. So there are two friends, and they have been caught for cheating in the exams. Right. Now, to remember a bit. Now, the invigilator takes both of them to two different rooms. So, why two different rooms? Because they are not able to communicate with each other. So, there's no cooperation. There's only they are all by themselves. Now, what the invigilator does is it offers to A this following deal. Right? So, if you confess that you have cheated, and if B does not confess that he has cheated, he or she, I'll let you go with only 1 point deduction and deduct 10 points from B. So there is always there is some reward for confessing. Ideally, both of you have cheated, so both of you have to be punished, but your punishment is less stringent because you have confessed, and that fellow has not confessed. Right? If both of you confess, then I deduct 5 from both of you. And similarly, if you don't confess, but the other guy confesses, then I deduct 10 from you, but only 1 from him because he has confessed. Okay. And if nobody confesses, then I only deduct 2 points from each. Now this is the, so here what you are getting is a cost, or so it's negative. So negative of these numbers will be the utilities. So what would be the players here? Two. So A and B. What are their strategies or actions?
Confess or
Either to
stabilize.
confess or not confess. And what are the strategy profiles?
Confess, not
Confess,
confess.
So there are four possible strategy profiles. Either both of them do not confess, one of them confesses, the other does not, or both of them confess. These are the four possible strategies. And these are the utilities corresponding to the strategy profile for player one. So for player one, if both of them do not confess, then there is a deduction of 2 points, so -2. If player one does not confess and the other confesses, there is a penalty. So there's a high penalty. So there's a deduction of -10. And if the other person does not confess and I confess, so I am good enough, so -5. And if both of us confess, then there is -5. Similarly, we'll have for the other player. It's there's a typo here. Yes. So in this, I think this will be 10. You two, if he confesses,
Yes.
-1. Correct.
Minus
If
10.
he doesn't confess, you are receiving -. That's a typo. Okay.
Marking mode.
Achha. So, So the gamma. So this is essentially the gamma here.
Like it was.
65. I hope the gamma is clear. N is the number of agents, S is the strategy profile, U are the utilities. Okay. So this is tough. I have to uncheck it, but that was not happening previously, right? Okay. So and this is the matrix that we have. So let me know if there's any confusion or any difficulty in reading the matrix. Two players and their corresponding utilities. Okay, this is the next game. Okay, in this case, what do you think the players should do? Should they confess or should they not confess? Both of them should confess.
Ideally, if they're each as an individual approach, one should confess to reduce its marks and get the highest degree of -1. But if other confesses, then it will get -1.
Imagine if I confess, if I don't confess, and I am playing for this -2, -4. The son will confess. No. So it's better that I confess. So if you don't confess or stay quiet, I am better. Both the confessing.
So should we both confess?
Yes.
Yeah.
Or should we both not? So both not confessing is giving both of us strictly lesser cost, like -2. But the moment both of us don't confess and you betray me and you confess, then I am the one who is getting caught. Right? So if I'm the role player and I decided not to confess, and I assume you also don't confess, then both of us are at -2. Right? But the moment you confess, right? So the column player betrays the row player and shifts to confess. Now, what is the utility of the column player? The row player. The utility is decreasing by a lot, right? -10. So this is how you sort of read these utility matrices, and you should always focus on the first thing for the row player and the second for the column player. Change in strategies for the row player, change in strategies for the column. Let's go to the next game, which is the Pigou's network. So this is the precursor to the Brazes paradox. Pigou studied a simpler network and tried to model the traffic flow here And the more complex network is the Brazes network, and that I have put it in the assignment. So if you understand this network well, the problem set you can. Right? So there are two roads. One is a highway, and the other is a local road connecting cities Ahmedabad and Gandhinagar. I guess we have more than two roads, but sure, let's just get it. Keep this for now. On the highway, it takes 1 unit of time irrespective of the amount of traffic. So the idea is to have a very large highway so that it can hold a lot of traffic. So irrespective of the amount of traffic, everybody takes just 1 unit of time, could be 1 hour, 1 minute, 1 second, or one. So I mean, with a super something, it will be very fast. So on the local road, the time taken is proportional to the traffic. So if n number of vehicles or agents decide to take the local road, then out of total n, there are NL agents who are the fraction of the agents who are taking the local road is NL by n, and that's the amount of time that they to reach the other end. So in the worst case, what will it be?
Still one.
Yeah, in the worst case, it's still one. Right? If all of them decide to take the n, it's still. So what is the strategic form if there were only two agents who were trying to go from Ahmedabad to Gandhinagar or Gandhinagar to Ahmedabad?
Yeah.
Yeah. So you have two agents again, and the number of strategies again is two. Either you take the highway or the local road. And you have four possible strategy profiles, and you have utilities. So now how do you define the utilities for two agents? So if both of them take the highway, so this I have only written for one agent. So for that particular agent, the time taken is 1. So there's a negative utility of 1. And if the other one takes a local road and I take the highway, it's still -1 because highway is -1 irrespective of the traffic. And if I take the local road and the other one takes the highway, then it is -half. Can somebody explain why?
So there are two budgets. Only one person in a two road.
Right.
The capacity is 2, only one has one.
Yes. So NL is 1 and capital N is 2. So 1 by 2, half. And if both of them take the local road, and it's minus. Similar, you'll get almost similar values for the other for the second agent as well. Okay. And this is the matrix representation of the Higgs network. So if there were n agents, now how do we write the strategy form? So you have n agents, and your strategy set is HL. Now, what is the size of the strategy profile? N cross n?
N cross n.
2 cross n?
N square.
Okay, 2 to the power n. So for each of the agents, there are two possible options, H or L. So you have n possible agents. So 2 times 2 times 2, 2 to the. And this is how you will define the utilities. So for utility of any agent I, for a particular strategy profile S. So S is the big set of strategy profiles, which means every possible strategies that each of the agent is taking. Out of all those strategy profiles, I have picked one S, right? If I pick one S, that means I have fixed the number of agents who are taking the highway and the number of agents who are taking the. Now, what is that number? So NLS for a particular small s, NLS is a fixed number. That's the number of agents who are taking the local. Now, if these are the many people who are taking the local road, and I also decides to take the local road, then this is the utility that it will face for choosing the local. Is it clear? Minus NL by N. And irrespective of the number of agents, since highway is always -1, if I decides to take the highway, it's always -1. Now, there is a slight change in the rules. Now, what if player 1 must decide first? What if I say that this is not happening simultaneously? What if I say that player 1 decides first? Can so first of all, what I'm trying to say is that so in this particular form of representation for a game, there is no way to show which agent is going first or which agent is going second. This is all in a simultaneous way, where all of them are taking the same actions. But what I'm trying to say is, what if player one decides to go first? Based on his decision, I make a decision. So my strategies and the entire way in which you try to decide how the game works will change. Right? So for that, what we do need is a newer representation of a game. This representation of a game is not sufficient for us. So for that, so all the players are playing simultaneously in this particular setup of game, and each player has a fixed set of strategies or actions. Now, what can happen is, if you make a move first, there could be a game where you make a move first and I go next, and I have now a bigger set of actions to take. And once I take an action, again you probably have your turn and you have some other set of actions. So now in the setting of normal form or a strategic form game, it does not give us the leeway to define all of this, different number of actions at different time step and all that. So now what we need is a newer form of representing game. And for that, what we introduce is the extensive form. For that, let's first start with a game, which is an entry game, and then we'll try to see how we can have a new modeling for such a game. So in an entry game, firm A is already in the market and is making a profit of 2. Now what happens is, there comes some smaller firm. A is like a very big firm, Google or something. Now firm B is trying to enter into or mark into the market or opt out of it. So firm 2 right now has 2 options, either to enter into the market or opt out. So if firm A accommodates firm B, right? If firm A does not put a fight and just accommodates firm B, then both share the profit equally. So firm A was making a profit of 2, now each of them will make a profit of 1. But if firm A decides to fight, it does not want any more competitors, so it decides to fight. And now, because of the maybe fight would be anti-publicity and things like that, for all of that, they incur some cost, and that cost is 1. Right? Both of them incur a cost of 1. Now, and in the process, not just incur a cost of 1. Now since firm B has somewhat moved into the market, firm A loses 0.5 of its profit to firm B. Okay. If so, is the game clear? So there is a market or there is a firm already and it's making. Yes. Question, please. Okay, if there are no questions. So the game is that there is already a firm which is making a profit of 2. Now firm B is trying to enter into the market or opt out. If firm A accommodates firm B is very happy entering, and both of them share the profit. If they put a fight, then both of them incur a cost because of the fight, that is 1. And on top of that, firm A also loses 0.5 of its profit to firm B. So can you, okay. The idea is now to design an extensive form game representation of this particular entity. Now, so the idea is, so who is the one who is making an action first here? Right? Because A is already there, it's not doing anything. B is making an action. Either it is trying to go ahead with its business, opting in, or just opting out. Once it opts out, then there is nothing for A to do. It's just out of the way. But if it opts in, then either A can fight against it or accommodate. Right? And for that, we have corresponding utilities or payoffs defined here in the bottom. So all the leaf nodes define your utility. So what are actions here? How many actions does B have? 2. And how many actions does A have? 2. And how many strategies does B have?
B has checked.
Okay, so we will really understand what is strategies here. So strategies must always lead to a particular outcome, and you have only 3 outcomes in this case. So you have like two. So either B is out, or if B is in, A fights, B is in, A accommodates. These are the 3 strategy profiles that you have. Had I represented this in the strategic form or the normal form, how many strategy profiles would you have got? Yes. So then you would have had to represent 4. And how would you fill out the matrix? Can you all fill out the matrix? If I had written it in the strategic form. A, let's say, is our row player, and B is the column player. A has 2, which is 5 for a accommodate, and B has 2, which is out. Okay. Now, if A fights and B is out, what would be the utility for A? And what will be the utility for B? If A accommodates and B is out, and in this case, I think we can just copy the one below. So if A is fighting and B is in, so A gets a 0.5. So even if A goes next, the utility, the second utility is for the second player. So the first utility is always for the first player, which is A, and the second denotes the utility for the second player, which is B.
Both are for 0.5 loss.
So why? So the thing is, it was making a profit of 2. It incurred a cost of 1 because of the fight, and it also lost 0.5 because of 0.5 profit 2.
Why B gets minus 5 because B is profit.
B also incurs a loss of -1 because of the -1 because of the fight, and gets a profit of 0.5. Is it clear? So here this is 0.5 and this is 0.5. This is 1 and 1. They equally share the profit if A accommodates B. So this is the corresponding strategic form. This is not the corresponding strategic form. This would have been the strategic form had we thought of this as a simultaneous game. Okay. So so how do we define an extensive form? That the graph was just a representation of it, but the actual definition for the actual definition we need a bunch of things. What we need is the set of players. We also need to know who moves when and what are their actions. We need to know what players know when they move. So the idea is in prisoner's dilemma. I don't really know if the other agent has confessed or not confessed. Right. So if I had to draw a prisoner's dilemma, three for prisoner's dilemma. Okay. So there is this agent A. There is this agent A. Either he confesses or he does not confess. And based on that, the other player is taking the action. But the idea is the other player doesn't know where the player stands, right? Has this player confessed or not confessed is not known to the player B, right? So this particular level is indistinguishable to the player. Now, based on irrespective of where the player is, he also has only 2 options, that is either to confess or to plead. Here you will have the utilities corresponding to it. So the idea is, this is B. But B does not know if it is in the non-contest or contest. So this is in this. So the idea is we need to know what players know. Does player B already know what E's action was, or does it not know what E's action? That is something that we need to set. And then the players payoffs as the function of these strategy profiles, just like in the previous case. We also need to know the terminal history of play, in which case would be the leaf nodes, which will be the possible outcomes that are possible in this particular strategic form. And then we'll also define what strategies are in some time. So the set of players here is denoted by this. The action available to each player I is denoted by AI. So for example, in the entry form game, the action for B was to opt in or out, and the actions for A was to fight or accommodate. Z is denoted is there to denote the leaf nodes or the terminal histories, which essentially gives the utilities for each of the players that are involved. And what is P? SV. So P is when will each player play? So this assigns a sub history to a particular player. So in the beginning of the game, there's no history. We denote that as epsilon, which is empty history. And P of epsilon represents the player who is going to move first when nothing has happened. P of epsilon essentially represents the player who is going to move first. And once epsilon is done, then that particular player must have taken some action, right? Either confess or. So here it's epsilon. P of epsilon denotes, let's say, the player. So for example, in the entry form game, it was player B who was making the first action. And after that, after epsilon, maybe the player B had made an action of going in, like moving into the market. So in. Now after P of in, now it's player A's turn to make a decision. Right? So, or even P of out would also correspond. So these are sub-histories. One particular action after the. And UIZ denotes the utility to player I at each of these at the end. C is the terminal history, remember? So at the end, what is the utility that each of the player gets? That is denoted by UI of C. And there is one more important thing. This will actually help us define what strategies are in an extensive form game. That's called the information set of a player I. Now, what is an information set of a player I? It is a set of decision nodes that are indistinguishable to a player. Right. So in the entry form game, so okay, so how many in the entry form game that we had? We'll probably define the same game in the next. And so here, for example, I hope this is visible. So this is the previous tree structure that we had. Let's just go over the. So here we had two agents, and the action for A1 was accommodate and fight, and action for A2 was in and out. And the number of terminal histories are 3 here, which is in, accommodate, in, fight, and out. These are the 3 terminal history names that we have. P epsilon is 2. Okay, sorry. So A is 1 and B is 2. And P in is 1. P out will also be 1 there. And let's look at what information sets up. So for the first agent, so P in, so after, so A, the idea is 1 is A and 2 is B. Is it clear now? Okay, yes, I think here, so information set for the agent one are the set of nodes that is indistinguishable to the agent. So here I think so P of out in fact is not agent one. Can you tell me why? Because after P of out there is no more action that is happening. So P of in is one and P of out is not a history, valid history, because there is no more action that is happening. So I2, information set for 2 is the starting epsilon set because the agent 2 is going first. And for agent 1, there is only one place where agent 1 has to decide. That is after agent 2 has played in. Right? So that's the only set in its information. For another game, I think it will be more complex and it will be more clear. And these are the utilities corresponding to the sets of actions that are available, the sets of strategies that are available. Yes. Yes. Okay. So what you are trying to sorry. So here what you are trying to say is you have a B. B takes 2 actions out and in. After in there was A. What you're saying is after out there is a C. So at which you mean in this P or in the Z? Z is just the terminal histories. It's just the end that I'm doing. It's the outcome, the different possible outcomes of the game. There are 3 possible outcomes. Okay. Maybe we could take some time. If anybody else has any doubt here.
I think that information is an action taken at these levels.
No, it's this set of nodes that is indistinguishable to a particular player, by which I mean that every time I have to take an action, I'm at a particular node, right? So what are these different possible nodes where I am supposed to take an action? That is what is my information set. Wherever I am liable to take an action, that is my. Now, it could happen that, let's say, if firm A did not know what firm B is doing. Let's say if firm A did not have the information about which action firm B had taken. It could have firm B could have either been out or in. In that case, for the next agent, for A, out and in would be indistinguishable. Right? So both of them will come together in one information. So that's the idea. So in the next game, it will be more clear. Yes.
So let's say if we responded to A set, so will we modify the information set of B?
Yes, it will. So let's say if B, let's say, responded to A's actions by taking, let's say, some other action 1, action 2. Here also it took action 1, action 2. Now, what would be the information set? What would be the information set of agent 2 or B? That would be, so it has epsilon. It has fights. So after A has put up a fight, it has to take an action. It also has accommodates. There are 3 elements in its information. these are different possible nodes that are indistinguished. So that basically agent 2 queries about where I need to take an action. So in is for I1, right? So information set, this is only I'm talking about second agent. What second agent has to do? First of all, second agent has to second agent is in this particular set where it has to initially take the actions. For that, epsilon is there. And after when second agent has to, so after first agent fights, it has to take some action. Or if first agent accommodates, it has to take some action. So these are the cases where the second agent must take an action. So those are the nodes that is indistinguishable to the second agent. Now, if I modify this game and I say, agent 2, while again coming or responding to agent A, it does not know if agent A has put up a fight or accommodate. Let's say in a situation where these two are indistinguishable to this particular agent, then what will happen is I'll still have two decisions to make. One is in the beginning of the history. The other is in this particular node. Now this node, it does not know if it is here or there. Right? So all you can just club all of this, and this becomes one particular node. So then what I'll write is FA, fight accommodate, becomes one node in which agent 2 has to make an action. Because now agent 2 doesn't know if A has put up a fight or account. So now there are only two elements in the information set. One is in the previous, one is in the beginning. The other is in the next when A has taken an action. I just don't know which actually it is. Is it clear what information set is?
But it's not actually if it was the code thing,
If it was okay.
then
If
it would have been fight accommodate because it needs to.
yes, because if it has, then it can do two different things, right? Had it put fight and it could have taken two different actions. Had it put accommodate, could have taken two different actions. Now, there are two things that two different modes or different kinds of places where it has to take an action.
It's not in its control.
The definition said that decision is a unique sequence of actions from the root.
Yes.
So, like, I'm trying to.
Let me just go back to whether.
No, it's for this example. Like,
Okay.
by the definition. So, if I were to make information set of A now, after I know A1, A2 sources, A1, A2 are suppose they're identical. Like for Python accountant, B has put in there.
Okay.
So I have to like find A1 and find A2 and accommodate A1 and accommodate A2 as information set for I1, or will I write just A1 and A2 as information set? So the information set.
So here, information set for one is still in.
Yes, suppose it's if I wanted to form it correct.
So you're saying there is we are extending the tree.
Yes.
Okay. So we are extending the tree now.
So like now, will I write find A1 A2, accommodate A1 A2 in the information set, or just A1 and A2 in the information set, right?
No, just A1.
But and there won't be unique sequence actions from both, right? Since A1 and A2 are identical into final.
Okay, let's just write the tree properly.
In the accommodate won't be again even A3.
No, he's just given the same name.
Yes, but like actions of B in both cases are even A2. Even if A5.
So B, let's say now B is. So what you're saying is now B is taking an action.
Now A will be.
Oh, sorry. A and then B. Right. And now A has a, let's say, some action.
We don't need to name it. It's not important.
It's not, so you don't want to worry about how. Okay.
So now, if
What is
anyone
the,
needs
now what do you want? Information set for A or B?
information set for A?
Information set for A, right? Now, information set for A would be, first of all, in is there, or it has to take an action when A has taken fight and B has taken A1. That would be 1. A has taken fight, B has taken A2, that would be 1. Accommodate A1, accommodate A2. There will be 4. Yes.
That could be like equal fight.
Yes, yes. Because for A, all of them are indistinguishable. Yes. Okay. What would be the sub-history after? So there are, after fight accommodates.
First of all, they get like that.
Epsilon. Then there is in, out, in fights, in accommodates, in fights, A2, in fights, A2, A1. Sub-history is to reach to the leaf node every path, the path from the root to any particular node.
The path is also stored in the
The path is also stored in the information set. Yes. So it will be part of the info. So for every information set, you will have to define a particular play action that the player has to take. Okay, let's go for a newer game and see what. Okay, so for utilities are clear to all of you, right? So always remember, A is the first player, B is the second player. So first is A. Now let's go for a different game, which is matching pennies. So in matching pennies, what happens is there's a player 1 who wants the coins to match. Both of them are flipping a coin, head or tails, unbiased. And agent 1 wants the coins to match. That it gets a utility of 1 when both are head, and it does not get, it gets a negative utility of 1 when one is head, the other is. But the 2 does not want the coins to match. So for that, the matrix looks like this. This is the static form representation. Both of them are playing simultaneously. And both of them are playing simultaneously. Agent 1 has 2 actions, 2 possible outcomes. Let's stick to actions here. Either it could be a head for its coin, or it could be a tail for its coin. And similarly for the other agent. If both are heads, then player 1 is getting a benefit of 1, and player 2 is getting a benefit of -1. Getting a utility of minus, and so on. So this is the game of matching pennies. Now, so there is 2 variants of it. One is matching pennies without observation, when both play simultaneously, and there is the other variation where there is an observation. So two plays after one's toss. Okay? Two tosses after one's toss. Now, for both of these games, we can create an extensive form representation. Right? So, extensive form for without observation. This is how the tree looks like. 1 tosses the coin, gets a head or a tail. Now it's 2's turn. But since this is without observation, 2 does not know whether the outcome for whether the action taken by 1 was head or tail, because it does not, so without observation. Now it takes HMP and 1 minus 1. These are the utilities directly I have populated from the previous. Now, what would be the extensive form of this game? So, how many, so we'll always start with the number of agents. There are 2 agents. Yeah. So there are 2 agents, and the actions of each of these agents are H and T. So what would be the information set before we look at what the answer is? What would be the information set for agent 1? So information set for agent 1 would be epsilon. And what would be the information set for agent 2? So how many, what would be the cardinality of the information set for agent 2? 2? Because this is without observation. So agent 2 doesn't really know if the agent 1 has taken the action H or T. So the number of, so the nodes at which it has to take an action is just one for practical, for all practicality. So it's just combined H. Because it is not able to distinguish between these two. Think about it. So terminal histories are 4, the 4 possible terminal histories. And this is the player assignment. Beginning of the game, 1 place, and then 2. There are different sub-histories where 2 has to make an action. And this is the information set of each of the players. Any doubts, any questions? People online, this is a good time to ask. Are they even there? Okay. Anybody has any doubt or questions?
No question, ma'am.
Okay. Either all of you are not listening or I'm very clear. There is a chat. I think that was their discussion with you. And then I think these are easier things to deal with, utilities. So please ensure that the information set is clear because now we are going to use that to define what strategies are. So, but what about matching point, matching pennies with observation? With observation, what will change? Yes, right. So with observation, everything will almost remain the same except the information. So you again have 2 agents, 2 actions each. Terminal history also remains the same. These are the player assignments. And now the information set of the second agent has 2 different nodes. One is at H, the other is at T, because now it knows what the player, what player 1 had, what was the outcome of the toss of player 1. Was it head or was it? So at head, it will have to toss, at tail, it will have to. That's how you sort of think about it. These are the corresponding units. Okay, so this brings us to this new definition of something called perfect and imperfect information. So what is perfect information? Each player can observe all the previous moves. That's perfect information. And imperfect information is that at some point, if I'm not able to observe, maybe in the first round, I can observe the entire moves that player 1 has, but maybe 2-3 times we play and then I cannot observe. So at any point of time, if you're not able to observe what the previous player has made, what move the previous player has made, then that is called a game of imperfect information. So perfect information is you need to know what player 1 has played at any point of time, at any point of. Now, what is formally? How does that reflect in our mathematical definition? So here is if an extensive form game with perfect information is one in which all the information sets are singleton. So can anybody tell me why this corresponds to perfect information? At a perfect information, all the information sets are singleton. So in the previous game, we had matching pennies with observation, where both the players could see each other's. So here there were two information sets of agent 2, and both of them are single. But in the previous example of without observation, here there was one information set of agent 2, and the cardinality is not, the cardinality of that set is 2. It's not a singleton set. Because now it's not able to distinguish between these two actions of agent 1. Right? So whenever this cardinality is 1, that means it knows where it is at this point, or what the previous player's action was, and therefore that game would be a game of perfect information. Here the cardinality is 2. This is not perfect because agent 2 does not know if agent 1 has. So what about, yes. Yes, no, then it is imperfect. So perfect is only when at every point you know what the previous player's moves was. If there was at any point you didn't know what the previous player's move was, then it is an imperfect information. Perfect means complete knowledge. If partially you know, partially you don't know, that is imperfect. Yes, then it's an imperfect. So what is chess? Is chess a perfect information game or not?
Perfect.
Perfect. Tic-tac-toe? The cross and. What about cards, poker?
Imperfect.
Can you give me more examples of imperfect information games? Sorry? Oh, I don't I don't know all those games.
Name the column other person. Bingo.
Okay, okay. I did play bingo, but I don't remember. Any more games? Nobody is speaking from that side of the class. We should reshuffle.
Is lottery perfect or imperfect?
So what is lottery? So how do you define the game of lottery? What are the number of agents? What are the number of
All people who are bought the lottery ticket are agents.
are they?
Only the lottery
So in a
machine-
lottery, what would be the number of agents and what would be the actions? And what would be the sorry, what? Why is it imperfect? Because I can see what your die's output was. If you didn't, so just like coin toss, right?
Yeah.
Replace the coin. So you can have with observation, without observation. But by itself, it's not a
Then the lottery is also perfect.
lottery is also fine.
Because we know the outcome.
Let me
If
think
dice are
about lottery.
perfect, lottery is also
Okay. So in lottery, what will be the number of agents? The agents, let's say, is all the players who are trying to buy the ticket. And
I think so they only get
so,
number.
and their actions are, you'll have to bid for a number, right? Some number, let's say 1 to 1,000. All of their actions are this. And now, if the outcome was, if the, okay, in the lottery, there is actually, there is a particular agent who is actually choosing the number also, right?
I think so he's only there.
You should also include him as a player. And now, based on what his outcome is, your own utilities would be defined, but his utility is not defined. How do you
He
represent
has
this
to
as a
bid the-
game?
He has a negative utility, no?
Why? Oh, because he's paying you? Okay, sure. That's
No,
one way
but
of
if
thinking
no one
about
has
it.
that number. Imagine no one has that number.
Then I'll get to keep this. My utility is 0. I'm keeping my money.
The lottery guy gets more utility.
So if I get my own money, why will I? So that's nil.
You have to buy a ticket.
Oh, okay. Interesting. You're including more components to the game. Nice. Sure, I'll put that as an assignment problem. Let's see how people model it. Okay. So Prisoner's Dilemma was a game of perfect information, right?
No, imperfect.
Imperfect.
No.
Okay. So at least two of you are paying attention. Matching pennies with observation, perfect information. An entry game was also perfect. Chess is perfect. So now let's come to the other part. So in the matrix form games, strategies and actions were almost the same. Right? So in a matrix form game, what we had action 1, action 2, action 1, action 2. Now these were actions for the row player and these are the actions for the column player. And because of these actions, each of them got some utilities. And these directly led to a particular outcome. Made an action, got an outcome. After the other person also makes an action. But here in the extensive form game, if one player makes an action, doesn't get an outcome, you'll have to wait for what is, of course, you'll have to wait for what is the action of the other player. But you might always also have to act again. And finally, after a lot of things, such interaction, finally somewhere you will get an outcome. So actions in an extensive form directly does not lead to a particular outcome. It's a sequence of actions that this particular player has to make that will lead to an outcome. Now, so when all does this player have to make an action? At every information set that it has to make an action. Sorry. Now, after you define what is an action at all of those levels, that is when you come up with a strategy, because that is when you come up with the outcome. I'll define that here. This is one wrong. So what is a strategy? Strategy is something that leads to an outcome. Right? Keep that in mind. So in normal form, every action led to an outcome because, of course, everybody has to act. After everybody has made an action, makes an action, you come up with an outcome. But in extensive form, that's not the case. You keep making actions at every point of time. So all of that has to be factored in before you think of what the outcome is or what your strategy. So now how do you define a strategy? Is the set of actions that a player takes at each information set. And also the action at an information set should be available for that player to take, right? So you can have different sets of action that I can do at different information. For example, in the entry game that we were discussing, at first instant, it had this action of choosing in and out. And way below, we defined some A1 and A2 and A3 or something like that. So there are different sets of action that it has to choose. So what is the formal definition of a strategy? A strategy, SI of a player, is a function that maps information set to a particular action. And that particular action must be available to the player. So now SIJ for every information set. So now the information. So in this II, the capital I, it defines the different information set that is available with this agent's one. Right? Now let's take J to denote each of these information sets that are available to this agent. Now for all of those information set J, I define this term called CJ. Now CJ is the set of actions that are available to player I at an information set J among all the. And now strategy must select a particular action that is available to this particular agent at that information set J. So if we look at this game of, it will be more clear if I actually write that game down. So initially firm B, I should get an iPad. There's a firm B, it makes an action in and out. Firm A fights, accommodates. Oh, this is a, okay. Now firm B again has A1 and A2. Now, what is the information set of agent? So, what are the information set of agent B? Now, agent B has an information set of
I learned it's not and how by
epsilon,
by
5,
is there one
accommodate. These are, let's assume that it's indistinguishable. So, these are the three. Now, at epsilon, what is Cj? When J is it, then J is epsilon.
in and out?
In and out are the possible actions. So now now the strategy profile has to map epsilon to either in or out. Right? And when J is F, the A1 and A2 are the strategy profile. Now, so J is essentially trying to represent each of the information sets available to the agent, and S is a strategy which is mapping each of these information set to a particular action that the agent 2 must take. Is it clear? Yes.
C is the set of strategies. C is
Set
the
of
outcomes.
actions. C is the set of actions available to player at a particular information set. At the particular information set J.
See, this is a bit of AI.
If you consider AI to be the entire,
Let me map it something.
that's the language. So CG is the subset of, and it's I'll have to include that as well. Yes.
Like
It's
information set in
you're thinking in Python terms, is it? In that dictionary?
something like a value pair. It's like every information pair has a set of access.
Yes, exactly. You can think of it like that. But this is actually potential for all possible actions. But the strategy is picking one of them. By the time I learn how to operate this thing, you guys will learn it too.
But strategy is not a sequence of action. It's just one action.
But information set will determine the sequence of action. Right? Because in the first, when the time is beginning, epsilon, I took some action. Then when A takes one of these actions, what is my action? So it's the entire possible sequence. It will be very clear in the very next slide. So matching pennies with observation, you have these information sets, epsilon with observation. So I have all singleton information sets. And player 1 is, now this is the strategy for player 1. So player 1 is the first player who is tossing the coin, head or tail. So now what is the possible strategies? In the first, it could either be head or it could be tail. So S11 and S12. These are the two possible strategies that the player could have. But now for player 2, things become interesting. So now what happens is, for each of these information sets, and we have the figure as well. So So player one. So player one in the beginning has two possible 30. That's it. But now player two, to define a strategy, player two has to make two decisions. If player one had heads, what should I do? Should I do heads or should I do tails? If player one has done tails, what should I do? Should I do heads or should I do tails? So there are twofold decisions that I make, and this leads to four possible strategies. So if I play hedge when player one plays hedge, if I play hedge when player one plays tail, so I play hedge when player one plays hedge, I play hedge when player one plays tail. So that is one strategy. That is one strategy I could use. Or the other, and so on, you list all the other strategies. Right? Wherein player right. So I'll play hedge when player one. If player one was playing hedge, I'll play tail when player one was playing tail. The other. So strategy. So now, given this strategy, I know what to do. So what would be the end of the outcome of it? Right? So any confusion, any doubt? So now this is the corresponding matrix form of the matching pennies with observations. Now, if I had to write a corresponding matrix form of this extensive form game, now player one had only two strategies, either to play heads or tails. But now player two has four different strategies too. If depending on its information. Now, two information sets and two possible actions at each information set. So now I have four possible strategies. Now, and I'll populate the strategic form corresponding. The values of it. If player two had three possible actions to take, right? If player two could do heads, tails, and I don't know, body, something, HTB, right? What would be the size of the, what would be these strategies? How would the strategies look like? How many strategies will it then have?
See. So we have had respect for the
So if player, my question is, player one has two strategies, HM. But now I'm saying player three can have H, T, or B. Three possible strategies for every action that the player one takes. So now how many strategies can player two have? Player two. Player three. There is only two players. There are only two players. I'm just saying that player two now has three different actions. H, T, and B. So how many strategies can the player have?
eight.
Eight? Six? Or number without? 2 to the power 3.
We carry it.
Okay, sure. Anybody from online? So is everybody asleep there? Is this the previous slide? Okay.
Yeah, this one. Next.
Okay, think of the answer at home. Huh? One minute. Is it? How? Why? Sorry for who doesn't understand Hindi. Why only 4?
Actually, so outcome say different to actually like outcome.
No, I'm just talking about strategies. I'm not talking about the outcomes at all.
Strategies are the like sacrificing that lead to an outcome. So
So the different possible strategies that I can. So when one takes H, I could take H or I could take A. Now I could also take B. And with that, I'll also have HTB here. So there'll be a total 9 strategies. Okay? So HTB, T, HTB, B, HTB. Wait, where is your maths? Basic maths. Okay. Okay. Now let's look at this game. How many information sets and how many so write all of the things that you guys already know. I think I've already written it down for myself so that I don't get confused. Achha, before, how many do you think that strategic form is enough? Because every extensive form, I can write these strategies and I'll write the strategic form. So let's forget about the extensive form. Let's just stick to the strategic form and do all our analysis in that and work with it. Is strategic form giving me any more information, or is extensive form giving me any more information, or is it should I just stick with the strategic form? Visualization is better in it. So what I'm asking about is it telling you something more than the strategic form? No. Can we have a same strategic form representation for 2 different extensive form games? No. Really think about it. You should do your problem sets today so that you will know the answer for this question. If there can for every extensive form game, you have a certain strategic form that you can define. That's correct. That's great. That's drilled in your head. But now what my question is, can there be 2 different extensive form games? Right? There are 2 different trees that I draw. And they have different meanings. You can keep the same, but I change, maybe I'll put some I'll change the information set somehow. But the strategic form of both of them now is same. Is it possible or not? Do the problem set, you will know. Hey, for this game, tell me how many agents? 2 agents. And what are the actions for each of them?
For one is CD and GH.
For one is CD and GH. Let me just write that down. What is the information set for agent 1? From this side, I want more answers, please. Epsilon, and then you have to, that is actually denoted as C, comma E. Because and what about the action information set for agent 2?
Epsilon.
What? Yeah. What? Now, how many strategies would agent 2 have?
So let's see, it is
Two strategies. How many strategies can agent 1 have? So strategies for agent 2. So what is a strategy? Strategy is something that maps an information set to an action. At C, agent 2 has two possible actions, E and F. So it can be it can be for this information set, it can either be E. And for this one, epsilon. At epsilon, it has to take a possible action, which is C or D. And one more thing is that C and E, it has to take a possible action, G or H. Now at epsilon, it could take C, and here it could take C. Here it could take E, and here it could take C. Here it could take G, D, and here it could take G. So 4 possible strategies. So I hope the guys who have joined online are following. Do let me know if there is any doubt regarding what information set is, regarding what strategies are, what is an extensive form, what is a strategic form.
G then H.
Instead of C, what is T?
C, I think it will be H. Sorry. Is anybody trying to talk? Raise your hand. I mean, online.
Can you explain this strategy form, ma'am, again?
The strategies, the different strategies you mean?
Yeah. So means how this strategy C to H and D to H and then D to G. How this happen?
So for the agent 1, at the beginning, it could take an action C or D. So I selected C here for the strategy set. So in strategy 1, agent 1 is taking an action C in the beginning. And after agent 2 has taken an action E, agent 1 is taking an action G. So that's what is strategy 1. Every time agent 1 follows strategy 1, it will take an action C in the beginning, and then it will take an action G whenever agent 2 plays E. Now, in the next strategy, what it does is, it will again take an action C in the first time, but in the next time, when after agent 2 has played E, it will take an action H instead of G. So these are two different strategies that agent 2 can follow. Similarly, the third and fourth are when agent 1 is taking B,
There will be no action.
then there will be no action, but we have to define the entire possible mapping from the information set to the actions. That's how the strategy space is defined. The utility, what would be the outcome of such an action once the D? It will always be 2, 0, irrespective of what the action is. The outcome will be the same, but for the for the sake of it, we'll have to define the entire space of strategies that is possible.
We'll say the number of strategies for one is 4.
Yes, we will. No, we will say the number of strategies of 1 is 4, But the utility that corresponds to both of these strategies is the same, because after D there is no more game anymore. So the utilities will be 0, but the number of strategies are still 4. That's how the definition works.
Cardinality for player one will be correct.
Cardinality of no, that's not the right way of saying it, but outcomes you can say. Distinct outcomes. The distinct outcome that is possible for the player 2 is only 3. Player 1 is only. So the strategies essentially are trying to say what are the different possible actions that player 1 can choose at different stages of where it has to take an action. So that's how strategies are defined. Now, if I have to write a strategic form for this, what would I do? I'll just put S21 here, S21 here, S22 here, sorry, S11, 12, 13, 14, S1, S22. Now, if player 1 plays S11 and player 2 plays 2-1, what would be the utility for player 1? So he's taking E. Sorry for the bad handwriting. And C. So C, then E. Because he has taken E, now this fellow is taking G. So now you have 1, 2. Right? That's how C, E, and G. So this is 1, 2. So player 1 gets a utility of 1 and player 2 gets a utility of 2. Now, if player 1 is taking so player 1 is taking C, and then player in this strategy is 1, 1. And player 2 is now taking F. So now player 2 is taking F. And then it doesn't matter. So and then it doesn't matter what the player 1 is doing. So this will be the utility. 3, comma. Now, in this particular strategy, which is S12, player 1 is taking C first, and player 2 is taking in 2-1 E, and then player 1 is taking H. So here it will be 0, 0. And whenever player 2, if player 1 is taking C again, but now player 2 is taking F, so here it will be 3-1. So can you fill? You can probably now fill the rest of the. Next all is 2, 0. Okay. Let me show you the example. So here we had made this particular circuit observation. Skip that. I hope the strategies are clear to the people, to the one who was asking online. Okay. Now I have a different game. Where there are again 2 players. 2 is taking this action. A1, A2, A3. There are 4 actions that 2 is taking. And for 1, it does not know what action 2 has taken. So it's imperfect game. And now one has two different actions. H, D, H, D. This is -1. Sorry. Now for this game, what would be the strategy? What would be the information sets? What would be the number of agents? Blah blah. All of that. Try to write it down. And then, so that's compare that strategic form that you got with this strategy. Everybody agrees that this game is different from the game for matching pennies with observation. That game looks very different. So what would be the corresponding game of this? Matching pennies with observation is that agent 1 is taking 2 different actions. And now agent 2 with observation, so agent 2 knows where. And so now agent 2 is also taking 2 different actions. And then you will have some utilities, whatever. So these two are very different looking extensive forms. Now try to write the strategic form game for this and see how it looks. Do it, and you'll have more doubts. Yes.
Does this dashed line indicate that it is without observation?
It is without observation. Exactly.
Okay.
Just come back. I share the slides. So how many? There are 2 players. Actions for player 1 is 2, H and T. Actions for player 2 is 4, A1, A2, A3, and 4. What about the strategies? What about the information set?
information set for two is hexagon,
Epsilon only.
and information set for one is
A1,
A1, A2, A3, A4 in a single. Right.
So how many strategies would one have?
for one.
Only two.
Only two
Only
strategies.
two. Head and tail.
Head or tail. So you put one here, keep two strategies, head or tail. And how many strategies would two have?
Four.
Four. A1, A2 for epsilon A1, A2. So keep that A1 here, A2 here, A3 here. Will the matrix look the same?
Yeah.
So can two different extensive form games have the same strategic form representation? So definitely extensive form games tell you a lot. They are good to look at. And they give you more information and the dynamics. But for since there is a corresponding strategic form to every extensive form game, what we usually do is we do a lot of our analysis on the strategic form games. Try to understand what each players will do and what would be the outcome of the game. And then that would anyway correlate with the corresponding extensive. So from next class onwards, we'll only be focusing on strategic form games, and we will try to analyze different strategic form games and try to see what is a good outcome, what is the definition, what does it even mean for an outcome to be good in a strategic form game and all those things. Right? So, but still doesn't mean that extensive form games are useless. They have more information because it's not unique representation of it. So that's something you should yes.
One question. So we said that all of these extensive form the same strategic form.
Yes.
But the strategies themselves are like different. Even though the table looks exactly the same, strategies themselves are like different forms.
The strategies are like it's just about the name that we give. Right? It doesn't really matter. So of course it is different. It is different. That's the entire point. The fact that it is different, but the table looks the same. So if I give you these two matrices, will you tell me that they are different? Anything other than the names? No, right? You cannot really tell me that there is actually an underlying entirely different games that are happening. But what you can only see, so what I'm trying to say is strategic form is hiding a lot of things. You'll agree. That's why you're saying that they are different, but the matrix representation looks the same. So next class we'll see what is what is utilities are actually used for, what is rationality, what is intelligence, and then we'll look at how to really come up with the best response. If this is the matrix, I know it, you know it. What should I do? What would be my best response? What does it really mean to be? What does best response really mean? That's what we'll try to define. And then eventually lead to equilibriums and things like that. But it will be great if you guys go today itself and try to solve the problem set. Let me put it up here. Okay, what's the So this is the problem set that I have given you, right? So today we saw this game called Pigou's network. It's called Pigou's network, right? This is a slightly more complex form of the same traffic modeling that we had. So here we have two additional roads, and then these are like the highways, unit cost, unit time, no matter what, but these are like the fractional time. And now I want you to write the strategic form of the game and what is the utility utility of the agent when they go via the interface. But now I'll just modify the same traffic example with an additional road. Now this is a super speed highway. It's like zero. It's teleport. It's a teleportation device that we have in place. Now you have three different ways. So in the previous one, you had all the agents had two possible actions: go via V or go via W. But now you have three possible actions. That is, go via V, W, V to W, and it's directed. Probably it's not visible so much, but there is a people cannot go from W to V, only V to W. So three different actions. Now, what are the corresponding utilities for all that? That is something I want to talk. All I've shown is two-player games. All the games today had only two players. But what if I had three players? And each of the players have, let's say, three different actions. How would you represent that in a static form? Will one matrix suffice? Okay. So what you typically, so that's something that you need to, you need, so if there are three agents, you cannot really represent that in a, let's say, three-dimensional or something like that. So what three-dimensional essentially means is that, putting one of the agent's strategies as constant. So what that would be is essentially something like so many things that I need to figure out. So yeah, this is also important. So you need to look at these further reading and try to see if you can. No. Initially, I mentioned which chapters of these book, right? Yeah. So you can just read. Yeah. Let me just start. Okay, now I need to. I'll show this later. Let me just go here. So you have a matrix for player 1, player 2. Each of these actions, let's say player 1 has 2 actions, player 2 has 2 actions. Now for this matrix, I shift player 3's action as, let's say, H. So this is action, H is A1 is action 1 for player 3. So this matrix represents what is the utility that player 1 gets when player 1 plays action H, T, H, T, and player 3 plays it. So there will be a 3 value in each of these. Now you will also have a second matrix where player 3 is now playing action 2. And then you have all the possible actions of each of the players 1. So if player 3 has 2 actions, you will need 2 different matrices. And each of these will have 3 values because utility is corresponding to 1, 1. That's how you sort of. So this is like a 3-dimensional thing, but you're just showing it in. I think, okay, time's up, I guess. So that's it. There are other questions that I can sort of. So this is the prisoner's dilemma again, but I want you to, I'm saying that now they are going in turns. A chooses first and then B chooses. You have to write the information set and stuff like that. And then I've given the corresponding, I think I've already shown this to you in class today, so I guess you should be able to do it. This is the, so thank you guys for coming, and the next class is day after tomorrow, 10 to 4. Thank you everybody online. So the lecture.
We have the same thing as this one. This one because there was and this is the started. So what's the right?
Let me just go to that. Please, no.
Yeah, yes. That's fine. This one. For S13 and S22.
If player one is taking D, अच्छा तो two से नहीं होगा. So every time player one is taking D, you don't have to see anything.
For S22, it's a data show. It's still have the same value.
For S22, what is S22 here? S22 is F, right? But F can only happen when player one has
Yeah.
taken C. But since player one is taking D, so player two will only get the utility 0. Doesn't really have any
So
control. You'll just put 2 zeros everywhere.
About the stats.
Yes.
Like, so they what to like take into the
They represent that they are, yes, sorry. That the player who is supposed, it represents the information set, if you will. Like it's the one information set that the other player is facing, because it doesn't know where it is. For all practical means and purposes, for it, it's all the same scale that it is. Yes, we can do that. That essentially is what is happening in the information system. It's all getting combined in one.
But here it's like written such that settings are sort of linked.
Yes,
But
but
it's
they are
defined
not
as a path. in any
exactly.
case.
But for the sub history, now if player two had to take one more action, but player two you need, so then you will have to define the entire thing, right? Because player two knows what it has taken first and what player one has taken. So now what I have to do. So if you merge it in one and player two is again coming back, now what you do? How will you right? You're saying you merge all of this into one. Right? Now, if let's say I define a new game, that player two is again taking an action after player.
Okay.
In that case, if you merge all of it, but player two knows which action it had taken. So for it, all of this is different. So when player two comes again, just merging it won't stop. You have to have the tree complete. Thank you. Thank you.